Genius: The Life and Science of Richard Feynman by James Gleick. Picture this. It's just before dawn on July 16, 1945, somewhere in the New Mexico desert. While the world's brightest scientists are lying face down in the dirt, their eyes protected by thick welding glass, waiting for the culmination of a secret $2 billion project, one 27-year-old guy is sitting upright in the front seat of a weapons carrier. He refuses the dark glasses everyone's been handed. His logic? The truck's windshield will filter out the dangerous ultraviolet rays. He wants to see everything. After all, he's a scientist, and this is about to be the greatest experiment in human history. When the flash comes, it's brighter than anything ever witnessed. The earth turns paper white. The sky cycles through silver, yellow, then burning orange. But the first thing he sees is a purple blotch on the truck floor, an after-image seared into his vision. His scientific brain immediately overrides his stunned human brain, telling him to look up again. That's when he notices something nobody expected. The shockwave is creating clouds in the air. Something creates clouds, he thinks, his mind racing to understand the physics, even as this monstrous fireball climbs into the sky. That young man was Richard Feynman. While others in that moment thought of God, death, or the terrible power they'd just unleashed, Feynman thought about the beauty of the physics. One colleague would later describe him as half genius, half buffoon, a guy who could solve in his head equations that baffled entire teams of scientists, but who also played bongo drums, cracked safes for fun, and relentlessly poked holes in any kind of authority or pretense. Today we're diving into the mind of this extraordinary character, guided by James Gleick's national bestseller, Genius: The Life and Science of Richard Feynman. This isn't just a story about a scientist. It's about a completely different way of thinking, a way of being in the world that's filled with relentless curiosity, fearless honesty, and an unapologetic sense of play. By the end of our time together, you'll understand not just what made Richard Feynman a Nobel Prize-winning physicist, but what made him a true original, a magician, as his peers called him. You'll learn the secrets to his unique problem-solving approach, his profound understanding of what it really means to know something, and the simple but powerful lessons his father taught him that shaped his entire life. This is more than a biography. It's a blueprint for how to think for yourself. So how does a boy from a small town on the edge of New York City, a kid who fixed radios in his bedroom and was considered a mad genius by his high school classmates, become the most brilliant and influential physicist of his time? Richard Feynman's story doesn't start in some prestigious university lecture hall. It begins in a little wooden crate in his childhood bedroom in far Rockaway, a place that felt, as he said, like the end of the world. This crate was his lab, screwed together with switches and lights he'd wired himself, powered by old storage batteries he'd collected from around the neighborhood. His younger sister Joan was his loyal lab assistant, earning 4 cents a week to perform duties that sometimes included sticking her finger into a spark gap to get a mild shock for the entertainment of his friends. While other kids played baseball, a sport Feynman dreaded, he was taking things apart, radios especially. In the 1920s and 30s, a radio wasn't some sealed black box. It was a beautiful, messy diagram of itself. You could open it up and see the glowing vacuum tubes, the wires, the resistors. You could watch how the electricity flowed. To Feynman, the radio was a map, and he was obsessed with learning its language. He wasn't just following instructions, he was experimenting. If I do this, what will happen? This question, the motto of both a child at play and a scientist at work, became the driving force of his entire life. This relentless curiosity was a gift, nurtured by his father, Melville. Now, Melville Feynman wasn't a scientist himself. He was a struggling uniform salesman. But he had this deep fascination with the world and a profound philosophy of knowledge that he passed on to his son. Their walks together were lessons in really seeing things. Melville would turn over stones and talk about the ants, or point to the stars and wonder about the waves. He taught Richard a crucial lesson, one that would define his entire intellectual style. It's a story Feynman told many times. Another boy in the woods pointed to a bird and asked Richard, "What kind of bird is that?" Richard said he had no idea. The boy scoffed. "It's a brown-throated thrush. Your father doesn't teach you anything." But Melville had already taught him something far more important. He had said, "See that bird? In Italian, it's a ciutolapetida. In Portuguese, it's a bom de peda. In Chinese, it's a chunglongta. You can know the name of that bird in all the languages of the world, but when you're finished, you'll know absolutely nothing about the bird. You'll only know about humans in different places and what they call the bird. So let's look at the bird and see what it's doing. That's what counts." This was the core of the Feynman philosophy. Knowing the name of something isn't the same as understanding it. This idea became his razor, the tool he used to shave away jargon, pretense, and intellectual laziness wherever he found it. It's why he distrusted philosophy, which he saw as just a collection of clever words about other words. It's why he got so frustrated by how science was taught, where students would memorize a formula for energy without ever feeling the push and pull of the forces themselves. Another time, when he was a little boy pulling his red wagon, he asked his father why a ball inside rolled to the back when he pulled the wagon forward. His father said, "That, nobody knows. The general principle is that things that are moving try to keep on moving, and things that are standing still tend to stand still. This tendency is called inertia, but nobody knows why it's true." This was an even deeper lesson. Don't be afraid of saying, "I don't know." For Feynman, this became a source of power. Admitting ignorance was the first step toward genuine discovery. It was a release from the pressure of having all the answers. It was the freedom to ask questions, to be curious, and to doubt. This foundation, this love for tinkering, and this philosophy of true understanding carried him to MIT and then to Princeton. But even as he was mastering the highest levels of mathematics and physics, he never lost that playful, hands-on approach. He still saw himself as the boy who fixed radios by thinking. While his peers were becoming polished academics, Feynman remained the mad genius, a little rough around the edges, with a thick New York accent and a mischievous grin. When he arrived at Princeton for graduate school, a place of immense tradition and formality, he was terrified on his first day at the dean's tea. He didn't know the rules. The dean's wife asked him, "Would you like cream or lemon in your tea, sir?" He panicked and blurted out, "Both, please." She laughed and replied with a phrase that would stick with him for the rest of his life, a phrase he would later use as the title of his own book of stories. "Surely you're joking, Mr. Feynman." It was during this period, grappling with the frontiers of physics, that Feynman's unique genius really began to shine. He was working with one of the great physicists of the time, John Wheeler. The central problem tormenting physics was a deep flaw in their understanding of the universe. The theory of quantum electrodynamics, or QED, which described how light and matter interact, was a mess. When physicists tried to make their calculations more precise, their equations would blow up, producing nonsensical answers like infinity. It was as if the universe, when you looked too closely, stopped making sense. The greatest minds in the world, including Albert Einstein and Paul Dirac, were stuck. Feynman, still just a graduate student, decided to start over from scratch. He had an idea so radical, so simple, that it could only have come from someone who, in a way, didn't know any better. He proposed throwing out one of the most fundamental concepts in physics, the field. The field was this invisible, all-pervading medium that was supposed to carry forces from one place to another. Instead, Feynman imagined a world of pure action at a distance. "Shake this one," he would say. "That one shakes later. The sun atom shakes. My eye electron shakes 8 minutes later because of a direct interaction across." It was a beautiful, simple picture, but there was a problem. As Wheeler pointed out, it didn't account for how an electron, when it accelerates, radiates energy away and feels a resistance, a drag force from its own action. This was called self-action, the particle interacting with itself. To explain this, it seemed you needed the field. But then Feynman and Wheeler had an even crazier idea. What if the interaction worked both forwards and backwards in time? What if a particle in the present could be influenced by particles in the future? It sounded like science fiction, a blatant violation of cause and effect. But when they worked out the math, they found that this bizarre idea actually seemed to solve the problem. The influence from the future would arrive at just the right moment to create the effect of radiation resistance. This was the birth of a style of thinking that would become Feynman's trademark. He wasn't afraid of crazy ideas. He wasn't afraid to violate common sense. He followed the logic of his physical intuition wherever it led, no matter how strange the destination he was playing. And in this play, he stumbled upon a revolutionary new way of looking at the universe. This work eventually became his PhD thesis, but the ideas were so new and so different from conventional wisdom that he had trouble communicating them. The world of physics wasn't quite ready for him yet. And then came the war. In the spring of 1942, Feynman, like almost every other top physicist in the country, was pulled into the secret, urgent work of the Manhattan Project. He was sent to a remote mesa in New Mexico, a place that didn't officially exist, called Los Alamos. He was just 24 years old. Los Alamos was an extraordinary place. It was a hastily built town of mud and wooden barracks, surrounded by barbed wire fences. It was also home to the most concentrated collection of scientific brainpower in history. Oppenheimer, Fermi, Bethe, Bohr, the giants of physics were all there, working together with a single terrifying goal: to build an atomic bomb before the Nazis did. For Feynman, Los Alamos was both a playground and a crucible. He was put in charge of the theoretical division's computing group. In an age before electronic computers, this meant managing teams of people, mostly scientists, wives, who would calculate the complex equations for the bomb's chain reaction using mechanical calculators. Feynman, with his knack for breaking down problems and organizing systems, turned them into a human computer, a factory assembly line for numbers. But it was his playful, irreverent spirit that made him a legend. The military authorities at Los Alamos were obsessed with security. Every letter was censored, and all secret documents were kept in locked filing cabinets and safes. To Feynman, this was irresistible. He taught himself how to pick locks. He figured out the combinations to his colleagues' safes, not through any magical skill, but by observing human nature. People are predictable. They use birthdays or simple numbers. They write the combination down. Soon, Feynman was breaking into safes all over the lab, leaving little notes that said, "Guess who?" or "Nothing is secret." It was more than just a prank. It was a statement. It was his way of fighting against the pomposity and hollow authority of the military bureaucracy. It was a real-life demonstration of the lesson his father had taught him: always look past the uniform and see the person underneath. He became a thorn in the side of the security officers, but his scientific brilliance was so undeniable that they couldn't do anything about it. Oppenheimer, the director of the lab, recognized his genius immediately. "He is, by all odds, the most brilliant young physicist here," Oppenheimer wrote, "and everyone knows this." Hans Bethe, the head of the theoretical division and one of the world's leading physicists, took Feynman under his wing. They were an odd pair. Bethe was the formal, meticulous German professor. Feynman was the brash, loud-mouthed kid from New York. Their colleagues called them the battleship and the mosquito boat. Bethe would plow forward with a calculation, and Feynman would buzz around him, yelling, "You're crazy," or "That's nuts." But Bethe loved it. He knew that Feynman's fearless criticism and wildly original way of looking at problems were exactly what he needed. Feynman's time at Los Alamos was also marked by deep personal tragedy. His wife, Arlene, his childhood sweetheart, was dying of tuberculosis in a sanatorium in Albuquerque, 100 miles away. Every weekend, he would hitchhike or borrow a car to be with her. Their love story is one of the most moving parts of Feynman's life. Arlene was as spirited and unconventional as he was. She understood his passion for science, and she shared his disdain for pretense. She constantly reminded him of a question that became the title of his second book of stories. What do you care what other people think? She was his anchor, his idea woman, and his partner in all their wild adventures. Even as she grew weaker, they played games with the military censors, sending coded letters and jigsaw puzzle messages back and forth. Their love was a private world they built together against the backdrop of the bomb and her illness. Arlene died in June of 1945, just 1 month before the Trinity test. Feynman was by her side. He watched her last breath, and then, with the scientific curiosity that never left him, he noted the exact time on her clock. He later discovered that the clock had stopped at that very moment. A mystical person might have seen a sign. Feynman, the supreme rationalist, figured it out. The nurse, checking the time in the dim light, must have picked up the fragile clock and stopped it. He was devastated, but he returned to work. The bomb was nearly ready. The end of the war left Feynman in a strange state. He was a hero, one of the architects of the new atomic age. He was offered a professorship at Cornell alongside Hans Bethe, but he was also haunted. The image of the atomic blast, which had filled him with such scientific joy at the time, now gave him nightmares. He felt a deep sense of responsibility and gnawing anxiety about the future of a world with nuclear weapons. He also found that he couldn't work. For a scientist like Feynman, this was a kind of death. He called it the sickness. He had lost the pleasure of finding things out. He had all these job offers, this new fame, but the ideas wouldn't come. He would sit on the grass at Cornell and feel like a burnout. Then one day, in the university cafeteria, something happened. A student playfully tossed a dinner plate into the air. It was a Cornell plate, with the university seal on the rim. As the plate spun, it wobbled, and Feynman, watching it, noticed something. He saw with his physicist's intuition that there was a relationship between the speed of the spin and the speed of the wobble. He went back to his office and started playing with the equations for the wobbling plate. It was a simple, unimportant problem. But as he worked on it, he felt the old excitement returning. He was like a musician picking up his instrument after a long silence. The wobbling plate problem led him to think about the rotation of electrons, which led him back to the deep problems of quantum electrodynamics. The gate had opened. He was back. And what came next was the work that would win him the Nobel Prize. He returned to the strange, beautiful ideas he had developed at Princeton, his sum over histories, or path integral formulation of quantum mechanics. This was Feynman's grand vision. The conventional view of quantum mechanics was hopelessly abstract. It described particles as fuzzy waves of probability. You could never say exactly where a particle was, or what path it took to get there. Feynman offered a new picture, one that was both radical and profoundly intuitive. He said, imagine an electron traveling from point A to point B. How does it get there? The simple answer is, it takes every possible path. It travels in a straight line. It travels in a curvy line. It zips out to Jupiter and back. It goes backwards in time. The electron, he said, does anything it likes. This seemed insane, but Feynman showed that if you assigned a number, an amplitude, to every possible path, and then added them all up, you could calculate the probability of the electron arriving at point B. And the amazing thing was, this bizarre method gave the correct answers. It was a complete reformulation of quantum mechanics. Even more, it gave physicists a new tool, a new language for seeing the subatomic world. These were the famous Feynman diagrams. They were simple little stick figures, cartoons of particle interactions. An electron moving through time was a straight line. A photon, a particle of light, was a wavy line. When two electrons repelled each other, Feynman drew it as two straight lines, exchanging a wavy line between them. To other physicists, these diagrams were a revelation. Before, a simple calculation in QED could take months and fill hundreds of pages with dense algebra. Now with Feynman's diagrams, a graduate student could solve the same problem in an afternoon. Each diagram was shorthand for a complex mathematical expression. It was, as Julian Schwinger, Feynman's great rival, later said, bringing computation to the masses. The diagrams were more than just a tool. They were a new way of seeing. They turned the abstract, invisible dance of particles into something you could sketch on the back of a napkin. In the years that followed, Feynman's genius continued to roam across the landscape of physics. He developed a groundbreaking theory of superfluidity, the strange, frictionless behavior of liquid helium at near absolute zero. He helped create the modern theory of the weak force, which governs radioactive decay. And in the 1960s, as physicists were struggling to make sense of the bewildering zoo of new particles being discovered in their accelerators, Feynman came up with another simple, powerful picture. He proposed that particles like the proton weren't fundamental at all, but were made up of even smaller, point-like constituents. He called them partons. He didn't know what they were, but his model of these little hard bits floating inside the proton perfectly explained the results of new experiments at the Stanford Linear Accelerator Center. It was another case of his cutting through a complex problem with a simple physical image. His partons eventually merged with Murray-Gell-Mann's quarks to become the foundation of our modern understanding of matter. Through all of this, Feynman remained a teacher. His most famous educational achievement was the Feynman Lectures on Physics, a 2-year introductory course he gave to Caltech freshmen in the early 60s. He threw out the traditional history-first approach. He started with the atomic hypothesis. All things are made of atoms. And from that one sentence, he rebuilt the entire world of physics, from the simple to the profound, always with an eye for the deep connections between different fields. The lectures, published as the Red Books, became a classic, read not so much by freshmen, who found them too difficult, but by professors and working physicists, who found that Feynman was reshaping their own understanding of their subject. He taught his own children with the same spirit, urging them to find their own ways of solving problems and to never be satisfied with just knowing the name of a thing. He fought against the new math being introduced in schools, arguing that it was teaching children empty definitions and jargon instead of real intuitive understanding. In the last years of his life, Feynman took on one final, public role. In 1986, the Space Shuttle Challenger exploded 73 seconds after liftoff, killing all 7 astronauts on board. President Reagan appointed a commission to investigate the disaster, and Feynman, reluctantly, agreed to serve. Once again, he was the outsider, the naive technical fellow in a world of Washington insiders, generals, and aerospace executives. The commission's hearings were formal and slow. Officials from NASA gave polished, jargon-filled presentations. But Feynman was impatient. He started his own investigation, talking directly to the engineers and technicians, the people who actually built the shuttle. He quickly learned that the engineers had known about a critical flaw in the solid rocket boosters. The joints between the rocket segments were sealed by rubber O-rings, and the engineers knew that in cold weather, this rubber could lose its resiliency. It wouldn't spring back fast enough to create a seal, allowing hot gas to burn through. They had warned their managers, but they had been overruled. Feynman wanted to make this simple, physical fact clear to everyone. At a televised public hearing, while a NASA official was giving another evasive answer, Feynman did something extraordinary. He had asked for a glass of ice water. He took a small piece of the O-ring material, squeezed it with a C-clamp, and dipped it into the water. After a moment, he pulled it out and released the clamp. The rubber didn't spring back. It stayed compressed. He held it up for the cameras. "I believe," he said, in one of the great understatements in the history of technology, "that has some significance for our problem." In that one simple, hands-on demonstration, he cut through all the bureaucracy, all the charts, all the excuses. He showed the world the truth, not with a complex equation, but with a piece of rubber and a glass of ice water. It was the ultimate expression of the Feynman philosophy. He had once said, quote, For a successful technology, reality must take precedence over public relations, for nature cannot be fooled. It was his last great public act. Richard Feynman died of cancer 2 years later, in 1988. He had spent a lifetime dancing on the edge of knowledge, playing with the deepest mysteries of the universe. He had taught a generation of scientists a new way of seeing, and he had taught the rest of us a profound lesson about the value of a questioning, irreverent, and joyful mind. He left behind not just a legacy of scientific achievement, but a spirit, the spirit of the boy in his bedroom lab, forever asking, "If I do this, what will happen?" So what do we take away from a life like Richard Feynman's? It's easy to get lost in the sheer brilliance of his scientific achievements, to simply stand in awe of a mind that could operate on such a high level. But I think the real lessons of his life are much more accessible, much more human. They're lessons not about physics, but about how to live a life of intellectual honesty and boundless curiosity. The first, and perhaps most important lesson, is the power of thinking from first principles. Feynman had an almost allergic reaction to jargon, to borrowed knowledge, to what he called baloney. He had to build his understanding of the world from the ground up. This is what his father taught him with the story of the bird. Knowing the name isn't the same as knowing the thing itself. How many times in our own lives do we accept a definition or label as a substitute for real understanding? We learn a word like energy or inflation or love, and we think we know something. But Feynman would challenge us to put the word aside and describe the thing itself in our own language. This is incredibly difficult. It forces us to confront what we don't know, but it's also the only path to genuine insight. This is a practice you can start today. Pick any concept you think you understand, gravity, democracy, even your own emotions, and try to explain it as if you were speaking to someone who had never heard the word before. You'll be amazed at how quickly you find the edges of your own knowledge. The second lesson is the profound connection between play and genius. Feynman's stories of safe-cracking, drumming, and drawing aren't just charming distractions. They're the essence of his method. He saw everything as a puzzle, a game to be figured out. He approached a locked safe with the same mindset he brought to a difficult integral. He was always taking things apart, looking for the underlying mechanism, trying to find a clever, non-obvious solution. This sense of play kept his mind flexible and open. It protected him from the rigidity that can come with being an expert. It allowed him to ask silly questions and try foolish ideas. And more often than not, those foolish ideas led him to discoveries that the more serious minds had missed. The lesson for us is to not be afraid to be a beginner, to play with problems, to approach challenges with a sense of fun and lightness, instead of just grim determination. The most creative solutions often come when we're not trying so hard. Finally, Feynman's life is a testament to the virtue of what he called a satisfactory philosophy of ignorance. In a world that rewards certainty and confidence, he celebrated doubt. He believed that admitting not knowing was the only path to knowing. He was comfortable with uncertainty, with mystery. "I don't have to know an answer," he said. "I don't feel frightened by not knowing things, by being lost in a mysterious universe without any purpose, which is the way it really is as far as I can tell. It doesn't frighten me." This is a courageous stance, and it's more important now than ever. We're bombarded with information, with experts and authorities, all telling us what to think. Feynman teaches us to be skeptical, to question, to demand evidence, and to be comfortable with the fact that our knowledge will always be incomplete. He taught us that the goal of science, and perhaps the goal of a well-lived life, isn't to find the final, absolute truth, but to be engaged in the perpetual, joyful process of finding things out. That was a summary of Genius, The Life and Science of Richard Feynman, by James Gleick. We've journeyed through the mind of one of the most remarkable figures of the 20th century, but I'll be honest with you, a summary is like looking at a map of a beautiful country. The map can show you the landmarks, the rivers, and the mountains, but it can never replace the experience of actually walking the trails yourself. The real magic happens when you read the book. It's in the quiet moments, when a particular story or a simple phrase from Feynman's life hits you in a way you didn't expect. This summary is designed to help you decide if this book is worth your time. If anything we've talked about today has resonated with you, the curiosity, the playfulness, the relentless honesty, then I urge you to grab a copy. Reading it isn't just learning. It's an experience that can genuinely change the way you see yourself, the world, and the beautiful mystery of it all. The link to the book is in the description. Also, if you found this summary valuable, please hit that like button and subscribe to the channel. It's the best way to let us know you're finding value here, and it ensures you won't miss our next journey into another life-changing book from the billionaire's bookshelf. Let's keep growing together.